Captain Takeshi Yamamoto's tank had survived 3 months of combat in the Philippines. The Type 97 Chiha wasn't the most advanced tank in the world. Its armor was modest and its gun underpowered compared to American Shermans, but had been adequate against the weapons Japanese forces had faced. Infantry rifles couldn't penetrate it. Machine gun fire bounced off harmlessly. Even American anti-tank rifles required close range and perfect shot placement to be effective, which was why Yamamoto couldn't understand what had just killed Lieutenant Sato's tank. They'd been advancing through a rice paddy near San Manuel when American infantry opened fire from a tree line 600 meters away. Standard offensive action, small arms fire, and machine guns trying to slow the Japanese advance. Yamamoto's 3 tanks continued forward, their armor easily deflecting the rifle fire. Then Sato's tank, advancing on Yamamoto's left flank, simply exploded, not from artillery or aerial attack. There had been no whistle of incoming shells, no aircraft overhead. One moment Sato's tank was moving forward normally. The next, smoke and flames were pouring from a massive hole in its turret. Yamamoto ordered his remaining 2 tanks to halt and take cover. Through his vision port, he scanned the tree line, tried to identify what had destroyed Sato's tank. American infantry were visible, but they had no weapons large enough to threaten armor at this range. Then he saw it, a soldier standing partially exposed, holding what looked like a metal tube on his shoulder. The tube was pointed directly at Yamamoto's position. It looked nothing like an anti-tank gun, too small and too light to be a serious threat. The tube produced a flash and a trail of smoke. Yamamoto's gunner shouted a warning, but there was no time to react. The projectile struck the front glassy plate of Yamamoto's tank at a range of approximately 200 meters. The explosion was unlike anything Yamamoto had experienced. Instead of ricocheting or creating surface damage, the projectile punched through the armor like it wasn't there. Superheated metal sprayed through the crew compartment, killing his gunner instantly and wounding his driver. The tank's ammunition began cooking off, forcing Yamamoto to abandon the vehicle before it became a death trap. He crawled from the burning tank and took cover in an irrigation ditch, watching in shock as his 3rd tank suffered the same fate. Another American soldier with another tube weapon, another impossible penetration from a range that should have been safe. 3 tanks destroyed in less than 5 minutes by infantry weapons that looked like toys. When Japanese forces finally withdrew from San Manuel that evening, Yamamoto reported the engagement to his regimental commander, Colonel Hideaki Tanaka. The colonel listened with growing concern as Yamamoto described the American weapons. "You're telling me American infantry destroyed 3 tanks at ranges exceeding 100 meters using man-portable weapons?" "Yes, sir. The weapons appear to be tubes mounted on soldiers' shoulders. They fired rocket projectiles that penetrated our armor completely. I've never seen anything like it." Tanaka had received similar reports from other units. Japanese armor across Luzon was being destroyed by these mysterious American weapons, and nobody understood how they worked. The projectiles were too small to contain enough explosive to blast through armor by force alone. Yet they were penetrating steel plate that should have been proof against anything short of a direct hit from a large-caliber anti-tank gun. "We need to capture one of these weapons intact," Tanaka told his staff. "Intelligence has designated them as priority targets. Until we understand what we're facing, our armor is vulnerable." The opportunity came 3 days later when patrol recovered an unexploded American projectile from a disabled tank. The warhead was intact, allowing Japanese technical officers to examine it for the first time. What they found was simultaneously fascinating and terrifying. Major Kenji Matsuda was a senior ordnance officer for the Japanese 10th Division. He'd studied engineering at Tokyo Imperial University and had a solid understanding of explosives and ballistics. When the captured warhead arrived at his field laboratory, he approached it with scientific curiosity and military urgency. The warhead was surprisingly light for something capable of penetrating tank armor. Matsuda carefully measured and sketched it, noting every detail. The projectile was approximately 60 millimeters in diameter, with a distinctive conical shape at the front. The rear section contained what appeared to be a rocket motor, but the front section was a puzzle. "It's too light to be a solid shot," Matsuda told his assistant, Lieutenant Hiroshi Nakamura, and the explosive charge seemed small for achieving penetration through kinetic energy alone. There must be something else happening. He decided to cut the warhead open to examine its internal structure. This was dangerous work. The explosive was still active, but Matsuda had defused enough ordnance to be confident in his skills. Working carefully with hand tools, he began sectioning the warhead to reveal its secrets. What he found inside made him stop and stare in confused amazement. The warhead contained a cone-shaped cavity in the explosive charge, with the narrow end of the cone pointing forward. The cavity was lined with copper, precisely shaped and positioned. The entire design seemed backwards. Conventional shaped charges had convex surfaces, not concave ones. This makes no sense, Matsuda said, studying the cavity. Why would you create a hollow space in an explosive charge? That reduces the amount of explosive, which should reduce effectiveness. Unless... He pulled out his engineering textbooks, searching for any references to hollow charge designs. What he found was a theoretical paper from the 1930s describing something called the Monroe effect, a physics principle where shaped explosive charges could create jets of superheated metal traveling at extraordinary velocities. The principle was counterintuitive. Instead of using explosive force directly to penetrate armor, the shaped charge used the explosive to collapse a metal cone, converting it into a high-velocity jet that could punch through steel like a hot needle through wax. The jet's penetrating power came not from the explosive's force, but from the tremendous velocity and pressure of the metal stream. This is revolutionary, Matsuda said quietly, understanding flooding through him. Major Matsuda spent the next 48 hours conducting experiments to verify his theory about the shaped charge principle. Using captured explosives and copper from disabled equipment, he constructed crude replicas of the American warhead design. The tests were conducted at a remote location where failed experiments wouldn't endanger his personnel. The results confirmed his worst fears. Even his poorly constructed replicas could penetrate steel plate far thicker than Japanese tank armor. The shaped charge principle was real, and it was devastatingly effective. Lieutenant Nakamura watched the demonstration with growing horror. Sir, if the Americans have weaponized this principle in a man-portable system, our entire tank force is obsolete. No amount of armor we can practically carry on a tank will stop these weapons. Not just our tanks, Matsuda replied grimly. Every tank in the world. The shaped charge doesn't care how thick the armor is. The metal jet maintains its penetrating power regardless of armor thickness, up to several times the warhead diameter. A 60mm shaped charge can potentially penetrate 200mm of armor. Our tanks have perhaps 50mm at best. He prepared a detailed report for division headquarters, including technical drawings, test results, and a frank assessment of the implications. The report made its way up the chain of command, eventually reaching the desk of General Tomoyuki Yamashita, commander of Japanese forces in the Philippines. Yamashita read the report with a sinking feeling. He'd been expecting American technological advantages in areas like radar and communications. But a fundamental breakthrough in anti-armor weapons was something Japanese forces had no immediate counter for. Can we develop similar weapons? Yamashita asked his chief of staff. Major Matsuda believes it's possible, but it would require months of development and testing. We don't have months. The Americans are already using these weapons throughout Luzon. Our tank crews are reporting that their vehicles are being destroyed before they can close to effective firing range. Yamashita studied the tactical situation map. American forces were advancing steadily, and Japanese armor, which should have been a significant defensive asset, was being eliminated piecemeal by infantry armed with these bazooka weapons. Issue new tactics for our armor units, Yamashita ordered. They're to avoid engagement with American infantry at ranges beyond 100 meters. Use terrain for cover. Advance only when infantry support can suppress the bazooka teams. And prioritize capturing more of these weapons for study. If we can't develop countermeasures, we need to at least understand their limitations. But changing tactics in the middle of a losing campaign was nearly impossible. Japanese tank crews who trained to engage targets at medium range now had to operate at close quarters where American superiority in numbers and firepower was overwhelming. The shaped charge weapon had fundamentally altered the tactical equation. Captain Yamamoto, who'd survived the San Manuel engagement, found himself training new tank crews on the harsh realities of facing bazookas. Most of the trainees had never seen combat, and many still clung to pre-war doctrines about armor invincibility. Everything you've learned about tank warfare is obsolete, Yamamoto told a class of replacement crews. The Americans have weapons that make our armor relevant. A single infantryman with a tube on his shoulder can destroy your tank from 200 meters away. You cannot see the weapon until it fires. You cannot effectively return fire because you cannot identify the shooter quickly enough, and the projectile travels too fast to evade. A young lieutenant raised his hand. Sir, if a situation is hopeless, why are we still committing armor to combat? Because General Yamashita has ordered it, and because even obsolete tanks are better than no tanks at all. But you must understand what you're facing. The Americans have changed the rules of armored warfare. We're adapting, but we're adapting to a weapon we don't fully understand and can't match. Meanwhile, Major Matsuda was conducting further analysis of captured bazooka components. He'd obtained not just warheads, but complete rounds, including the rocket motors and firing mechanisms. What impressed him most was the system's elegant simplicity. Look at this design, he told Nakamura, disassembling a bazooka round on his workbench. The launcher is just a tube. No complex mechanics, no expensive optics, no heavy recoil mechanism. An infantryman can carry several rounds and engage armor with minimal training. The Americans have democratized anti-tank warfare. Can we copy the design quickly? The launcher, yes, we could fabricate tubes easily enough. But the shaped charge warhead requires precision manufacturing. The cone must be perfectly symmetric. The explosive must be uniformly distributed, and the standoff distance between the cone and the target must be correct for the jet to form properly. Our manufacturing capabilities are degraded after years of war. We might manage crude versions, but they won't match American performance. Matsuda's assessment was accurate. Japanese engineers did attempt to develop shaped charge weapons in early 1945, but the results were disappointing. Manufacturing inconsistencies led to unreliable performance, and the weapons that did work were produced in quantities too small to affect the strategic situation. Meanwhile, American forces were using bazookas with devastating effectiveness throughout the Pacific theater. Japanese after-action reports from Luzon, Iwo Jima, and Okinawa all mentioned the psychological impact of the weapons. Tank crews knew their armor provided minimal protection, which affected their willingness to engage aggressively. Private First Class Robertson was a bazooka gunner with the 37th Infantry Division during the Luzon campaign. He'd never seen the Japanese technical analysis of his weapon, but he understood its effectiveness from practical experience. We'd been told the bazooka could knock out tanks, but seeing it work was something else, Jim recalled years later. You'd fire this rocket that looked too small to hurt anything serious, and suddenly there'd be a Japanese tank burning. The crews who survived would just run. They knew their armor couldn't protect them anymore. Chen's assistant gunner, Private James Morrison, carried the spare rockets and helped load the weapon between shots. The Japanese were terrified of bazookas. You'd see their tanks stop advancing the moment they spotted one of us. Sometimes they'd retreat, even if we hadn't fired yet. Just seeing the weapon was enough to break their morale. This psychological dimension was something Major Matsuda had noted in his reports but couldn't quantify. The shaped charge principle didn't just defeat armor. It defeated the sense of invulnerability that armor provided. Japanese tank crews had trained with the understanding that their vehicles made them superior to infantry. The bazooka destroyed that understanding, turning armored warfare into a deadly game where infantry can engage tanks on favorable terms. By February 1945, Japanese tank tactics in the Philippines had evolved into desperate measures. Some commanders ordered their tanks to operate only at night, hoping darkness would make bazooka teams less effective. Others positioned tanks in static defensive positions where they functioned as pillboxes rather than mobile weapons. A few innovative commanders tried using tank infantry cooperation, where foot soldiers would engage American bazooka teams, while armor provided fire support from protected positions. None of these measures were particularly effective. The American advantage in shaped charge technology combined with superior numbers and logistics, made Japanese armor increasingly irrelevant to the campaign's outcome. Colonel Tanaka, who'd originally ordered the capture of bazooka weapons for study, met with Major Matsuda in March to discuss the strategic implications. "Your analysis was correct," Tanaka said. "We're facing a revolutionary weapon that we can't counter with current technology. What are the long-term implications?" Matsuda's response was sobering. "Sir, shaped charge weapons will change armored warfare permanently. When this war ends, every military will develop similar weapons. Tank armor will need to be completely redesigned, perhaps with spacing or reactive elements to disrupt the metal jet before it penetrates. Tank tactics will have to account for infantry being able to engage armor at ranges that were previously safe. And for us right now, it means our tanks are obsolete and our crews are dying in vehicles that can't protect them. The best tactical adjustment is to avoid armored engagements where possible and accept that infantry anti-tank weapons have shifted the balance of power." The captured bazooka and Major Matsuda's technical analysis made their way to Japan in March 1945, carried by submarine through increasingly dangerous waters. The Imperial Japanese Navy's Technical Research Department received materials with intense interest, recognizing that this technology represented a fundamental shift in military capabilities. Commander Yutaka Sato headed the naval research team assigned to study the shaped charge principle and develop countermeasures. Unlike Major Matsuda, who'd worked under field conditions with limited resources, Sato had access to proper laboratories and manufacturing facilities. But he also faced a more daunting challenge. The American technology was months or years ahead of Japanese capabilities, and the war situation was deteriorating rapidly. The Americans didn't invent shaped charges, Sato told his research team during their first meeting. The physics principle has been documented in scientific literature since the 1880s. The Monroe effect was described in detail decades ago. What the Americans did was weaponize it effectively in a man-portable system. That's the breakthrough, not the science, but the engineering. He displayed cross-section diagrams of the Bazooka Warhead that Matsuda had prepared. Notice the precision required. The copper cone must be formed to exact specifications. The explosive charge must be uniform. The standoff distance between the warhead and target must be correct for optimal jet formation. These aren't impossible requirements, but they demand manufacturing quality that our current industrial capacity struggles to provide. Lieutenant Commander Kenji Fujimoto, Sato's senior engineer, studied the diagrams carefully. "We can manufacture shaped charge warheads, sir. The question is whether we can do it in quantities and quality sufficient to affect the war's outcome, and whether we can develop effective countermeasures for our own armor." "Start with countermeasures," Sato ordered. "Our tank forces are being destroyed by these weapons right now. If we can develop armor configurations that defeat or reduce shaped charge effectiveness, that information could save lives immediately." The research team began systematic testing of armor configurations against shaped charge penetration. They fabricated crude shaped charge warheads based on Matsuda's analysis and tested them against various armor arrangements. The results were both illuminating and discouraging. Solid armor plate, regardless of thickness, was highly vulnerable to shaped charge attack. The metal jet could penetrate several times its own diameter in steel, making conventional armor almost useless. But certain configurations showed promise. Spaced armor, two plates separated by an air gap, disrupted the jet's formation and reduced penetration significantly. The first plate would trigger the warhead and form the jet, but the air gap would allow the jet to expand and dissipate before hitting the second plate. Reactive armor, explosive panels that would detonate when struck, could deflect or disrupt the incoming jet. These countermeasures work, Fujimoto reported after weeks of testing, but implementing them on existing tanks would require complete redesign and remanufacturing. "We don't have the time or resources for that." Sato had expected this conclusion. Japan's industrial capacity was being systematically destroyed by American bombing. Factories were operating at reduced efficiency, raw materials were scarce, and transportation networks were disrupted. Redesigning tank armor in these conditions was impossible. "Then we focus on understanding the technology for future application," Sato said. "Document everything we learn. When this war ends, whoever controls shaped charge technology will have a significant military advantage. That knowledge may be more valuable than any immediate tactical application. Meanwhile, in the Philippines, the ground reality was becoming increasingly desperate for Japanese forces. Captain Yamamoto's surviving tank had been destroyed in early March, forcing him to continue fighting as infantry. He'd witnessed firsthand how completely the bazooka had changed the tactical situation. "We used to advance with confidence," Yamamoto told a war correspondent who was documenting the Philippine campaign. "Tanks were mobile fortresses that gave us superiority over infantry. Now we're the ones hiding, trying to avoid engagement." A single American soldier with a bazooka is more dangerous to armor than an entire platoon with rifles. The correspondent, a civilian named Takashi Ito, was collecting information for a report that would never be published. The Japanese government had no interest in publicizing how thoroughly American technology was defeating their forces. "Do you believe Japan can develop similar weapons?" Ito asked. "Eventually, perhaps, but it won't matter for this war. The Americans have already won the technological race. We're fighting with weapons designed for the last war, while they're using weapons designed for the next one." By April 1945, American forces had nearly completed their conquest of Luzon. Japanese armor, which should have been a major defensive asset, had been largely eliminated. The few remaining tanks were hidden in caves or used as static pillboxes, their mobility and offensive capability neutralized by the constant threat of bazooka attack. Major Matsuda survived the campaign and was evacuated to Japan in late April. He met with Commander Sato's research team to share his field observations and tactical analysis. The meeting was both professional and deeply pessimistic. "The shaped charge principle is elegant," Matsuda told the naval researchers. "It converts explosive energy into kinetic energy with remarkable efficiency. The metal jet forms at velocities exceeding 7,000 meters per second, faster than any conventional projectile. At those velocities, armor behaves almost like a fluid. The jet doesn't so much penetrate as flow through the steel." "We've observed the same phenomenon in our tests," Sato confirmed. "The physics are well understood now. What we're struggling with is the engineering precision required for consistent performance. That's where the Americans have excelled. Their manufacturing quality ensures that every warhead performs reliably. Our attempts to replicate the technology have been inconsistent because our wartime industrial capacity can't maintain the necessary tolerances." The researchers discussed potential applications of shaped charge technology beyond anti-tank weapons. Naval mines using shaped charges could potentially penetrate ship hulls. Artillery shells could be fitted with shaped charge warheads for attacking fortifications. Anti-aircraft weapons might use the principle to defeat heavy bomber armor. But these discussions were academic. Japan's strategic situation in mid-1945 made advanced weapon development irrelevant. The war was being lost through industrial and numerical superiority, not technological advantage. Understanding shaped charge technology wouldn't change the outcome. In June 1945, Commander Sato prepared a comprehensive report on shaped charge research for the Imperial Japanese Navy senior leadership. The report was detailed, technically sophisticated, and brutally honest about Japan's inability to match American capabilities in this area. "The shaped charge represents a paradigm shift in armor warfare," Sato wrote. "Traditional armor design assumed that protection increased with thickness. The shaped charge makes this assumption obsolete. Future armor must be designed around defeating shaped charge jets through spacing, angles, and reactive measures rather than simple thickness. Japan lacks the industrial capacity to implement these designs during current hostilities, but post-war development should prioritize this technology." The report was filed and largely forgotten as Japan's military situation collapsed through summer 1945. The atomic bombings of Hiroshima and Nagasaki in August made all conventional weapons research suddenly irrelevant. Japan surrendered on August 15th, and the shaped charge research project was terminated. American occupation forces discovered Sato's research when they took control of Japanese military facilities. Intelligence officers were surprised by how thoroughly the Japanese had analyzed the bazooka's operating principles. Some of the Japanese countermeasure research, particularly work on spaced armor, was actually ahead of American thinking in certain areas. They understood the technology, noted a U.S. Army Technical Intelligence officer in his report. They just couldn't manufacture effectively or implement countermeasures given their industrial limitations. If Japan had discovered shaped charges first, or if they'd had more time to develop counters, the Pacific War's armor battles might have played out very differently. Captain Yamamoto survived the war and returned to Japan in late 1945. He'd lost his tank, most of his crew, and his faith in armor warfare as he'd been taught it. Years later, he reflected on the bazooka's impact during an interview with military historians. The shaped charge weapon changed everything we understood about armor, Yamamoto said. Before the bazooka, tanks were dominant on the battlefield. Infantry feared them. After the bazooka, tanks were vulnerable targets. The weapon didn't just destroy our vehicles. It destroyed the psychological advantage armor provided. Tank crews knew that a single enemy soldier could kill them from ranges where we couldn't effectively respond. That knowledge affected every tactical decision we made. The interviewer asked whether Japanese forces could have developed effective responses if they'd had more time. Perhaps, Yamamoto replied. Major Matsuda and Commander Sato understood the technology and proposed countermeasures. But understanding and implementation are different things. The Americans had the industrial capacity to produce thousands of bazookas and millions of shaped charge rounds. We couldn't match that production even if we'd understood the technology from the beginning. The shaped charge technology that devastated Japanese armor in 1945 continued to evolve long after the war ended. Commander Sato's research, confiscated by American occupation forces, was declassified in the 1950s and became part of the technical literature that informed post-war armor development worldwide. Major Matsuda returned to civilian life and became a professor of mechanical engineering at Osaka University. He rarely spoke publicly about his wartime experiences, but he did publish several technical papers on shaped charge physics in the 1950s and 1960s. His work, based on the analysis he conducted in that Philippine field laboratory, contributed to the broader understanding of high-velocity metal jet formation. In 1967, Matsuda was invited to speak at an international symposium on armor technology in Geneva. The audience included engineers and military officers from nations that had been enemies to decades earlier. During his presentation, Matsuda displayed the original sketches he'd made of the captured Bazooka Warhead in 1945. When I first examined this weapon, Matsuda told the audience, I was struck by its elegant simplicity. The shaped charge principle had been documented in physics literature for decades, but the Americans were the first to weaponize it effectively in a man-portable system. What made the bazooka revolutionary wasn't new science. It was brilliant engineering applied to a known principle. He clicked to the next slide, showing test results from his field experiments. I calculated that even our crude replicas could penetrate armor several times thicker than what Japanese tanks carried. That's when I understood we were facing not just a new weapon, but a fundamental shift in armored warfare. Thickness alone could no longer provide protection. The shaped charge had made conventional armor obsolete. An American engineer in the audience raised his hand. Professor Matsuda, your wartime analysis of shaped charge countermeasures was quite sophisticated. Your work on spaced armor predated similar American research by several months. If Japan had been able to implement your recommendations, how much difference would it have made? Matsuda considered the question carefully. Tactically, perhaps significant. Spaced armor and reactive countermeasures could have reduced shaped charge effectiveness by 50 to 70%. But strategically, it wouldn't have mattered. Japan's industrial capacity in 1945 couldn't support the manufacturing changes required. And even if we'd successfully countered the bazooka, America's overall technological and industrial advantages would have prevailed. The symposium represented a remarkable moment. Former enemies discussing weapons technology that had killed thousands, approaching the subject with scientific detachment and mutual respect. The shaped charge had evolved from a devastating surprise weapon into a standard component of military arsenals worldwide. By the 1970s, virtually every military force possessed shaped charge anti-tank weapons. The technology had proliferated beyond the original bazooka design into recoilless rifles, guided missiles, and rocket-propelled grenades. Tank designers responded with increasingly sophisticated armor packages, incorporating spacing, reactive elements, and composite materials designed to disrupt shaped charge jets. Robert Chun, the American bazooka gunner who'd fought in Luzon, attended a veterans reunion in 1978, where he met a former Japanese tank officer. The meeting was arranged by historians documenting the Philippine campaign, and both men approached it with some apprehension. The Japanese officer was Captain Yamamoto, now a successful businessman in his 60s. Through a translator, the two men discussed their experiences facing each other across the battlefield. "I remember when we first encountered your weapon," Yamamoto said. "We couldn't understand how infantry was destroying our tanks from such distances. It seemed impossible according to everything we'd been taught about armor warfare." Chun nodded. "We were just as surprised it worked so well. They told us in training that the bazooka could knock out tanks, but you never really believe it until you see a tank explode from your shot. The psychological effect went both ways. You were shocked your armor didn't protect you, and we were amazed we could kill tanks with a tube on our shoulder. Did you understand technology? The shaped charge principle?" "Not at all," Chin admitted. "I knew you aimed it, pulled the trigger, and the rocket went out and blew up tanks. The physics of how it worked wasn't something they taught infantry. We just knew it was effective." Yamamoto smiled sadly. "And we had engineers who understood the physics perfectly but couldn't do anything about it. That summarizes the Pacific War rather well. Japan had knowledge without resources, while America had both knowledge and resources." The conversation reflected a broader reconciliation between former enemies. The shaped charge technology that had been so devastating in 1945 had become a shared technical heritage, studied and developed by nations that had once fought bitterly over its application. Commander Sato, who led the Japanese naval research into shaped charges, lived until 1989. He watched as the technology he'd studied in desperate wartime conditions became ubiquitous in modern military arsenals. In his final interview, conducted by a defense technology journal, he reflected on the broader lessons of the shaped charge story. "The bazooka taught us that technological surprise can have strategic impact," Sato said, "but it also taught us that technology alone doesn't win wars." Japan understood shaped charge physics quite well by mid-1945. We had talented engineers who could replicate the technology, but we lacked the industrial capacity to manufacture at scale and the tactical flexibility to adapt our armor doctrine quickly enough. The shaped charge was devastating not because it was incomprehensible, but because we encountered it when we were least able to respond effectively. The interviewer asked about the post-war evolution of shaped charge countermeasures. "That's where the technology became truly interesting," Sato replied. "The arms race between shaped charges and armor drove innovation on both sides. Reactive armor, composite materials, active protection systems, all developed in response to shaped charge threats. The principle I studied in 1945 remains fundamentally the same, but the engineering around it has become extraordinarily sophisticated." Modern military historians studying the Pacific War have identified the bazooka as one of the most cost-effective weapons America deployed. The entire weapon system, launcher and projectile, was inexpensive to manufacture and required minimal training to use effectively. Yet it neutralized Japanese armor, a much more expensive and resource-intensive weapon system, with remarkable efficiency. The shaped charge principle that made the bazooka effective has applications far beyond military use. Modern mining operations use shaped charges for precision blasting. Oil and gas drilling employs shaped charge technology for well perforation. Demolition experts use shaped charges for controlled building collapse. The same physics that destroyed Japanese tanks in 1945 now serves numerous peaceful industrial purposes. In 2005, on the 60th anniversary of the end of World War II, a joint American-Japanese military history conference examined the technological developments that had shaped the Pacific War. The shaped charge bazooka was featured prominently in discussions of weapons innovation. Professor Hiroshi Tanaka, grandson of the Colonel Tanaka who'd first ordered capture of bazooka weapons for study, presented research on his grandfather's wartime experiences. Colonel Tanaka recognized immediately that the bazooka represented something fundamentally new. His decision to prioritize capturing and studying the weapon showed tactical foresight. But as Major Matsuda's analysis revealed, understanding the technology didn't provide an immediate solution. Japan's strategic situation made effective response impossible. An American presenter, Dr. Sarah Morrison, granddaughter of Private James Morrison who'd served as a bazooka assistant gunner, offered a complementary perspective. The bazooka's effectiveness came from combining existing technologies, shaped charges, rocket propulsion, and simple mechanical launchers, into a weapon system optimized for infantry use. It wasn't revolutionary science, but revolutionary engineering. That's often how military innovation works. Not through scientific breakthroughs, but through clever application of known principles. The conference concluded with a joint statement emphasizing that studying weapons technology wasn't about glorifying warfare, but understanding how innovation shapes historical outcomes. The shaped-charged bazooka had changed armored warfare permanently, forcing a fundamental rethinking of how tanks were designed and employed. Today, visitors to military museums can see examples of the M1 bazooka that terrorized Japanese tank crews in 1945. The weapon looks almost primitive compared to modern anti-tank systems, a simple metal tube with basic sights and a crude trigger mechanism. But that simplicity was part of its genius. It was a weapon that ordinary infantry could carry, operate, and maintain under combat conditions while delivering performance that rivaled dedicated anti-tank guns. Next to the American bazookas in some museums are examples of the Japanese shaped charge weapons they eventually developed. Crude copies that arrived too late and in quantities too small to affect the war's outcome. These weapons represent Japan's understanding of the technology and their inability to implement it effectively under wartime constraints. The story of the shaped charge bazooka offers lessons that extend beyond military history. It demonstrates how understanding technology differs from deploying it effectively. It shows how manufacturing quality and industrial capacity can be as important as scientific knowledge. And it illustrates how a relatively simple innovation, properly engineered and deployed, can have strategic impact far beyond its apparent sophistication. For those interested in exploring more stories about technological innovation that change the course of history, examining how simple principles combined with effective engineering can overcome seemingly superior forces reveals patterns that apply far beyond warfare. The shaped charge principle that Japanese officers discovered when they cut open that captured Bazooka Warhead in 1945 continues to influence military technology 8 decades later. Modern anti-tank weapons are vastly more sophisticated than the original M1 bazooka, but they operate on the same fundamental physics that Major Matsuda analyzed in his Philippine field laboratory. The elegant simplicity of converting explosive energy into a high-velocity metal jet remains one of the most effective methods for defeating armor, proving that sometimes the most revolutionary innovations are those that apply known principles in new and unexpected ways.